Well, my name is Eite Tiesinga. I'm happy to be here. I thank Dorte for the invitation. So I work at the place called the Joint Quantum Institute, which is a collaboration between the National Institutes of Standards and Technology and the University of Maryland. And I'm going to talk to you about, the first two words here are Feshbach, and that's the two-body part of it. But I really want to talk to you about the sort of like the matter wave analogy of slow light. A sort of more of a quantum optics view of cold atom physics. That's what I want to tell you about. So in particular, it's the control of the group velocity of atoms propagating through a Bose-Einstein condensate. Okay. Let me see if this works. There you go. About NIST, I always like to talk about where the place I work, which is a government lab. And so we have a mission to promote innovation by advancing measurement science, standards, and technology. So we're always thinking about standards. We were the original NBS. Okay, we're located here in Gaithersburg, there, just off half an hour from Washington, D.C. And this here is an aerial image of our latest new labs. There are actually 5 buildings, 2 of them are underground. Okay, standards. For me, I'm always trying to make the connection. Standard 1, calibrating tape measures of all kinds. That's why I have a nice image there of a 60-meter long tape measuring device. Is one application of what a standard is. Okay, of course I'm a physicist, so I will only highlight the physical standard, not chemical standards or biological standards or computer science standards. Right. So the other one, which is the hot topic in our field, maybe, is the prototype kilogram, which is an images. This is a kilogram. It's platinum and iridium, and made in 1889, and there's a big push to get rid of it. Okay, so NIST is involved in that. Not me personally, but NIST is.
There is no standard pound for the US?
Kilogram.
What
There's
pound?
the pound. No, the pound is out. Anything that's not the SI unit is out.
You would imagine that.
Yeah, this is the American one. And so sort of maybe getting closer to also what NIST does, and what I may be interested in is the fundamental constants. This is a photograph of the pocket-sized thing that you can get for your wallet with the best fundamental constants. And this is the transition from 2006 to 2010, and you see that the numbers and some of the constants have changed. I think even if you look at capital G, it has actually gotten worse in that time. So it doesn't have to get better, it might get worse, right? Okay.
So some of them are measured and some of them are defined in your track.
Correct. So indeed, the speed of light is defined, is one, and most of them are measured, have error bars on them. And so the thing about the kilogram is the push to make h bar equal to 1, or whatever number you like. Yes. So we want to get rid of the kilogram and replace it with h bar equals 1. If that's meaningful to you. And 1 probably has units, which is also a difficult subject. So for me, now we're getting to the cold atom part. Is the hot topic of the killer app for cold atoms is these atomic clocks. The best clocks so far at the moment, well, not anymore. I saw when I read the Physics Today a month ago, but the second best clock in the world is this particular clock. It's the NIST F1. It is a cesium atomic clock. So they measure the hyperfine splitting of the ground state of cesium to about 15 significant digits. Okay.
What's the temperature
in this clock? I don't know, a few microkelvin. It is not Bose condensed. It's actually, the goal is to make it as dilute as possible so that there are no collisions. This is the ultimate few-body system. You want to have it one only. Okay. It's not interesting to have interaction.
So they have 10 to -17 or -18 or something?
Not with this clock. This clock, this is the atomic cesium clock, it will have only 14, 15 significant digits. The optical clocks that are being built and pushed as the next generation clocks will have that accuracy, yes. And here's a more cartoonish picture of what's going on in these clocks, okay? So before I start with my actual talk, I want to highlight some other projects I've been involved in. This particular discussion will be a work by Ranshu Matthew, and you can find the article over there. With Phil Johnson and Dorte, I've been working on a few body problem with field theoretical tools, effective field theoretical tools. And so he talked about it last week, so I'm not going to talk about it here. But the basic idea is that we were looking at 3 and 4 body interactions generated by 2 body interactions, and in the context of cold atoms. With a postdoc, Paul Kahn Mahmoud, I've been looking at spinar condensation, or spinar gases, that are atoms with a magnetic moment, have 3 magnetic sublevels, and you can have interchange between them. Okay? Some graphs out of that. Some more collaborators, some students, where I've been looking at atoms and optical lattices. I've been also learning about fermions and the Bogubov-de Gennes equations. Looking at soliton physics with a professor at George Mason University. And finally, I've also doing helping experiments at NIST, and there was really a spinar condensate paper. That's here. Okay. Also have no time to talk about that. So motivation. What I was looking for is matter-wave analogs. Okay. So atom optics, if you like. And so the classic example is this image here, an experimental image of an atom laser. That is, you make a Bose-Einstein condensate of atoms, and I think this case it is rubidium or sodium, with sodium atoms, if you like. What you see here is either a pulsed laser that goes into a CW laser. Right? So the atoms are coherent. It's a single plane wave mode of atoms. Okay? That was the first application of an atom optics experiment. People are doing also sort of interference between Bose-Einstein condensate. This is actually showing that the laser is coherent. In this case, you have 2 condensates, you release them, they expand, they overlap, and generate this kind of striped interference pattern, showing that the condensate had a phase, or at least a relative phase, right? Maybe more exciting matter wave analog is 4-wave mixing. In this case, we really needed interactions. Okay, the atoms, the interactions give nonlinear interaction. That's nonlinear behavior. So the experiment was basically sort of, these are images, both I think experimental images, in 2 different pictures, are called lab frame and moving frame. The experiment was generate a Bose-Einstein condensate, a big Bose-Einstein condensate, kick 2 little pulses out of there in this momentum, and with that momentum, P1, P3 and P2. And out comes all of a sudden a 4th beam at a momentum given by this, which is the sum of all these momenta with signs. Okay? This is 4-wave mixing. In a moving frame, it's maybe more clear, where you have 3 clouds colliding this way and that way, and out comes something in that way. And these are experimental images.
But in the picture, you have 2 incoming, 2 outgoing.
Well, this one's at rest, so that's incoming too. Yeah, if I had made this picture, which I didn't, I would have moved this maybe arrow down there to make it more looking like incoming. So all the thick lines, the full lines are incoming, but this represents their momentum, and the dotted line is the outgoing beam. Okay. So you can do this with collisions. Okay.
So where do you need the collisions in there? I mean, this just looks like kinematics, right?
So yes, what we need, this process needs to be stimulated in that sort of light version. Sort of in the light, what you would, maybe you know the light version better. You need to have nonlinear medium in which you can have 1 photon in and couples with another photon. Is that helping? Maybe I should write down an equation for the normal equation of motion for light is the nonlinear Schrödinger equation, or for atoms is the nonlinear Schrödinger equation. Psi dot equals psi square psi with the strength. And then what you have to imagine is the origin of the 4-wave mixing is coming from imagining this wave function.
Then you have an idea.
Sure. Is expand this in these 3 modes. And for this to be be normalized to 1 of a sort of like of this form, you need a 4th momentum to make it sensible. That's the 4-wave mixing. Is that helping? The light equivalent is parametric.
If you set G to 0, you wouldn't have that.
Correct. That's the light. Yeah. I don't know whether this was helpful, but maybe things will become later more clear. So I wanted to look at something called slow light. The analog is here this particular light experiment. You have a dispersive medium, which is this square box, and you put in a light pulse. Okay, and what happens is this medium changes the propagation speed of the light pulse in this medium, and the pulse comes out delayed. Sort of this is what happens in free space. That's what's delayed, right? And the art.
Can I tell you that?
Sure.
So if you have that four-way mixing, three
Yes.
going to one,
Yeah.
you should have the reverse process too. So the reverse process, as far as I know, you see, nobody's seen, nobody talks about. So why you have it going in one direction, not in the other direction? Because obviously time reversal invariance is not broken.
What inverse experiment do you imagine?
No, you see, I start with one, and I should have three clouds, you see, because that's allowed again. You see, it's a time reverse process. So why, you see, it goes in one direction, it doesn't go in the other?
I don't think you can. So if this is my equation of motion,
You see,
not in this
I go
case.
Backward in time, you see, so I don't know what.
So for me, it's like a single condensate is stable, can't do anything. So it is not the time reverse process, the one that you described. You said
You see, because I take exactly the process, do time reverse, and you see, to the equation of motion, and I obtain exactly the opposite. So why that doesn't happen? So it's something strange here.
so the experiment was indeed you have three beams coming in, and they collide at some point.
I don't understand why the other one is not happening, so I suspect it's something which we don't understand in that process. Because it goes one way, it should go the other way too.
I'm not sure what the opposite experiment is yet. I haven't figured out what.
One should go into three.
One should go into three.
Yep, that's allowed.
A single condensate sits, doesn't do anything. You can move along with it, doesn't matter.
No, I don't know, you see, but if that's possible, the other one should be possible too. So it's
Oh, but it's
just
not the time reverse, because in one of the case you have zero kinetic energy, which is the one
Yeah.
at rest. The other one has lots of
That's
kinetic energy,
reference
yeah?
frame, you change the reference
No,
frame.
because
see,
you have-
Galilei invariance.
You have
see,
three
it's-
beams coming, you still have a lot of kinetic energy. It is not the inverse of each other.
No, I
You mean
don't agree.
phase-based? I mean, there's a phase-based issue.
You have a lot of maybe the momenta is adding up to zero, but the kinetic energy doesn't add up to zero.
Energy is conserved.
I agree.
Yeah.
That's true.
But the
So you-
forward process is not 3 to 1, it's 3 to 4. Right?
Yes.
It's 3 to 1.
It's
Just
3 to
one.
4.
Yep.
No, it's not. It's 3 to 4. You get a fourth beam out.
I'm sorry.
There still is four beams. It's not that all three are combined and going away, you just have one beam
But
out.
that was the impression.
No, yeah, that
Exactly.
figure was, I think, a little misleading.
Okay, so the figure was a little bit misleading then. This is what the final state. Actually, maybe I should have said what these images were. These are indeed after you start out with coming in with three beams. This is what comes out. There's the fourth beam coming out. There you
So
go.
it's really 3 to 4. So the
It's 3 to
inverse
4.
Process, if nothing else, would be have a base-based
Okay,
issue.
so that was not exactly what was explained.
Sorry. It's always difficult to be precise. Okay, so the origin of this delay is something about the index of refraction of light propagating for the medium being frequency or color dependent. So this is a sort of a schematic drawing of what that index of refraction is. So the idea is to have a light pulse with a frequency spread, a light pulse in time, a frequency the spread in frequency spread that fits in this region here, where the index of refraction is changing rapidly with frequency. If you happen to be able to do that, then you can make slow light or fast light or whatever. Okay? Okay? So in this case, what the origin is a resonant scattering of photons in the medium. The medium have transitions inside of them, and you resonantly scatter off of them. This is the origin of that index of refraction. Okay? So I want to look at the analogous behavior of atoms scattering with a Bose-Einstein condensate near a collisional resonance. Okay? There's a resonance in the collision. So this is for me the problem statement. I want to look at that particular experiment where I have a small moving Bose-Einstein condensate, which I will probably call laser throughout the talk, propagating through a large stationary Bose-Einstein condensate, which I probably will call medium in the analogy, right? And that hopefully this beam, when it passes through, gets delayed. So
Same atoms in both clouds?
Hmm?
It's the same atoms in both clouds or different atoms?
in the derivation I will give you, they are the same, but it doesn't truly matter. Okay, so this is sort of like the schematic picture. You have an initial BEC that propagates in free space. You have a pulse, a BEC scattering through and gets delayed. Okay, that's the ideal. The problem is, though, that I have to worry about this particular process, where a BEC at rest and a pulse comes in and all this stuff comes out in other directions that I really don't want. Okay. And the reason why I mention this immediately, because already 10 years ago they did an experiment where here's some experimental data of after the fact collisions where they indeed see these kind of halos appearing. The experiment was indeed with take two condensates that are about equal in size, shoot them at one another with controllable velocities, and look at the stuff that came out. And what they saw is that all these images are for different relative collision energy, ranging from 87 microkelvin to 348 microkelvin. This is rubidium, as it happens. And what they see is that for certain collision energies, you get this sort of asymmetric stuff coming out. And this is not what I want, because I'm losing a lot of atoms. I want to slow atoms. I don't want to have them go all over the place. Okay.
And you mentioned resonances. Can you say, I mean, if you're moving BEC, can your stationary BEC can be containing different atoms? Where do you want your resonance to be?
In the relative collision between the atoms. I'll have a lot more slides on the subject. So indeed, I want the collisional resonance between an atom from this cloud and an atom from that cloud. Okay? But this I don't want. This, by the way, is also, this effect here is actually also due to a resonance, but this is actually a shape resonance as opposed to a Feshbach resonance. Okay, so a little bit of background on what is a Feshbach resonance to me. It starts out with Feshbach and Fano, and mostly Fano in our field. And this image here is actually from his 1961 paper that is famous in atomic physics. And it explained the energy loss of forward scattering, what did I say? Forward electron scattering of helium, of atomic helium. Okay? So what you actually do is we temporarily form a negative ion. That's what these resonances are. Actually, I'm told from the paper that it's the 2s2p level that you populate in this particular energy domain. Okay? So that's an example of a Fano resonance or a Feshbach resonance. The other one that I always like to mention is sort of laser cooling, right? You scatter a light from an atom with photon energy that is a resonance with an atomic transition. Okay? In other words, laser cooling, we temporarily form an atom-photon complex, I will call it, or an excited state. Okay? In our case, what we want to look at is, I want to collide two ultra-cold atoms, and I want to temporarily form a diatomic molecule. Okay? That's my resonance. So what's so special about our resonances in cold atom physics? Because the resonances are everywhere. And so this is sort of my slide on that. First, you have to realize in cold atom experiment, it's actually very hard to change the collision energy. We don't really have accelerators or decelerators, right? And so I'm also the collision energy or temperature of the gas, except with what I'm going to tell you about, a little bit of control, right? I mean, change collision energy is always something relative to something. So in this case, what I mean, it's hard to change it relative to the natural energy scales of the collision potentials, of the interaction potentials. Okay? In this case, it's a discussion about the long-range van der Waals potential and what its energy scale are. And it's very hard to change collision energies relative to that. Okay? So what typically happens is we apply an external magnetic field and move energy levels up and down, and thereby control the resonance. Okay? But for me, what is crucial is that this happens near the edge of a threshold. And sort of that's what I was trying to show you in this figure, where here is this external magnetic field, here is energy, and this gray area is a scattering continuum of two scattering particles. This the red diagonal line is that molecular level that I'm going to be able to shift, right? It crosses through. When it's in this region, it's a resonance, When it's in this region, it's actually a true molecular state. It's stable. And so what I'm showing here in this blue line is sort of its width as function of where it is. And what you'll notice is that when the resonance gets closer to threshold, it gets narrower. Okay? In a way, maybe that's what you expect, right? The resonance needs to turn into a real molecule, so its width needs to decrease. Okay? But its width does it actually in a very curious way, and that's what this shows here. This is roughly the resonance location above threshold, and the vertical axis is its width, and I will call that gamma. Okay? It's all in microkelvin in this case. And what you'll see here is the black line is that width as function of energy. It is actually going like the square root of the energy. Okay? Actually, this actually isn't actually an existing resonance of rubidium-87 at 1006 Gauss. And what you notice is that this resonance has a width that is larger, that there is a region of energy here where the width is larger than the collision energy.
Are you considering S-wave resonance here?
Correct. Okay. Which is kind of curious. Normally when I'm looking at resonances, I'm always thinking that the width of the resonance is small compared to the collision energy. In this case, actually, what you can have situations where the width is larger than that. And so that's actually interesting. This is of the origin of being able to change the scattering length. Okay, okay, so I've said everything that I wanted to say there. Okay. You're right, the P waves, for example, do not have this property. Then actually it goes like e to the 3/2, and then there is never an energy region where the width is larger than the collision energy. Okay. Happy with that? So there are lots of other pictures, and for example, this molecular picture is what you typically see people talk about, is that you have two potential curves as function of the separation between the atoms, and you collide sort of like at that energy here. And then you have this other channel, which is called the closed channel, which has a bound state in it, and then it leads to a resonance at a certain energy. Okay? So you have three cases: a decaying resonance, on resonance, and a molecular bound state. Right? That's also a nice picture of other resonances. A third one that I sometimes like is this: when you place these two atoms in a harmonic trap, which we can also do, you get a sort of like the continuum discretizes into harmonic oscillator levels. That's sort of these, right? And this bound state here needs to like shift inward into it, and so pushes levels around a little bit, right? It's a way of thinking about it. And then when the resonance lies below threshold, it only pushes levels up a little bit. Okay. So one more slide on scattering that you need to know to see the rest of my talk is scattering length. For me, it's the effective size of an atom at zero collision energy. It's best introduced, for me anyway, so putting a hard wall at a distance a and positive separation here, and I can solve the Schrödinger equation for that problem. There it is. And I can think about what is scattering length. In reality, of course, things is more complex, and that's what this graph is. This is a far more realistic wave function of scattering of two cold atoms. Okay? Still, at large distances, I can fit it to a sine kr minus a, and then I have my definition of what a scattering length is. Right? What's neat is that it can be negative. And if you are into field theory, which most of you are, you tend to then all of a sudden throw this potential out of the hat and say this is the scattering length. Okay? And most of the time, these things are known to like 1% in our field. And they're typically measurements. Okay? So if you now scatter in a magnetic field, what you can do is you can change, due to the presence of the resonance, you can change the scattering length. And this is what this graph shows. As function of magnetic field, the scattering length. And you will notice that it's infinite at the resonance position. It approaches the background value away from it. And it's zero at something called B res plus delta. Okay. And then the form of this shape is sort of this resonant form, where it has a background scattering length, it has a width, and it has a distance from the resonance position. Okay, so most of you have seen that before. This was my work as a graduate student with my advisor and colleague. Okay? To go further, to do my problem of scattering to condensates at a hot temperature, I need to do better than the scattering length approximation. There's a resonance form. So I have to tell you a little bit about the shape of the scattering amplitude. Okay? And this is actually work that Fano and Feshbach did. This is this analytic solution for an isolated resonance. What they were able to set up is an analytic form of the scattering amplitude. And sort of there's your graph, right? You have a scattering center, you have a plane wave coming in from the left and outcoming spherical waves. And the amplitude in front of the circle wave is the scattering amplitude. Or if you like in Feynman-like diagrams or diagrams, this is the form, right? The scattering amplitude at the collision energy is given by the scattering without the resonance, which I call the background scattering amplitude, plus the resonance bits where I temporarily form molecules, they fall apart and do that stuff, right? And you can do that sum and you get sort of this formula. This is what I need for my discussion of scattering condensate. This is a slightly more involved formula. It has minus the background scattering length. It has a resonance shape, Lorentzian-like shape, dimensionless, and then there's 1 over k in front, which is the wave number. Then there's this width gamma that I showed you an image of already, right? And then there is this denominator. Plus now a resonance width that depends on energy, okay?
So you find the resonance now is a time, because you put h bar there. Right?
Here?
So typically the resonance width is defined as energy.
Oh, in my case, since I'm at NIST, we think about units.
Yeah.
Gamma is in our field typically per second.
Yes, that's what I'm saying.
So h bar, if you like, I don't know, just make the units correct.
But that's different from what typically people do.
I know. There's a lot of problems in our field about where is the 2 pi going.
That's typically referred as the rate, not the width.
Yes.
So that's I think it should be a different symbol, because the rate, you see, it's what you call gamma.
I agree. You should talk to Bill Phillips. He will like this a lot. He's worrying about these 2 pi's and stuff like that. It's people calling something that's oscillatory, exponentially decaying and
It's nice
stuff.
to follow them, you know.
Well, I mean, maybe you can go back to your slide that had the bits
Uh-huh.
and just clarify if that was an energy bits or.
There, I'm sure it says h bar gamma over k.
Just
Even
just to
you want to be sure. No, I forgot the h bar. Darn.
I think that's maybe where the confusion comes from. So
Yes. I thought on the talk it should be all right. I will change it to a h bar. Okay, so the resonance width actually can be expressed in sort of this golden rule thing, 2 pi times the square of a matrix element. Okay, and maybe again to remember is that it goes like the square of the energy. Okay, and this is maybe useful for those who like to follow the formulas later on. Okay, like a little bit of rearrangement. If you go to the limit of e to 0, you will actually get the minus a formula that I got you there before. I like to also note that, I mean, if this is not energy dependent and you convert this into the time domain, you get exponential decay. If you keep the square root of e behavior actually, and you are able to make the experiment, prepare the resonance, and then see how it decays, it actually decays polynomially, if that's interest to you. It doesn't decay exponentially. Okay, happy? Okay, so this formula was too complicated for me. I need a graphical representation, so this is a graphical representation of that formula. So this is the scattering amplitude as function of collision energy. But you realize the scattering amplitude is complex. I have a real and imaginary part. The blue stuff is real and the red is imaginary. And both have a beautiful line shape. But you have to already remember what is going to happen later on is that the real part of the scattering amplitude is going to be responsible for the slowing. The imaginary part is going to be responsible for losses. So I want no losses, but I still want to have a significant index real part, okay? Losses, real part, okay? Good graph? Okay, so remembering, this is it. I want to solve this problem, and I have to have a little bit of a moving laser BEC propagating through a big stationary BEC at a collision energy, which I'm going to call E collision, with corresponding wave vectors and velocities, right, K0 and V0. Just keep that in mind. So, this is now the technical part, hopefully in one slide. Description of a Bose condensate. So the normal thing to do is we assume as a chemist, I sometimes have a chemist head and say all particles are in the same wave function. That's what the first way of thinking about a Bose condensate is. Right? If you're more of a field theorist, you say that there is an order parameter, which is a wave function. Right? And then, as I tried to describe there, this typically satisfies something called the Gross-Pitievsky equation, or the nonlinear Schrödinger equation given here. It contains typically an external trap, a kinetic energy, and this interaction term, which is g psi squared psi. Okay? Turns out, though, near a Feshbach resonance, and where I want to do this is not sufficient, so I have to generalize this. Okay? And so the path we decided to take is something called the cumulant expansion method, as sort of pushed in this paper by Thorsten Köhler. In the essence, what you do is you say that the variances of more and more complex order get smaller and smaller. Okay? Variance, skewness. And so you work with that. The trick here now to realize is that the laser and medium BEC will occupy separate momenta spaces, because one is going to move and one will be at rest. Right? So in that case, the momenta do not overlap, and then I'm allowed to make this observation, that you split the wave function up in the medium and the laser condensate, right? And then what you can get is sort of like generalized interaction terms, something like, of course, the self energy of the laser with itself, the medium interacts with itself, but you also have sort of cross terms like this, that the laser propagation will be modified by the presence of the medium, okay? And after some work, we came up with this is the right way of expressing that. That is, how is the laser propagation modified by the presence of the medium? So all we had to do is generalize it to this form, where f is my scattering amplitude again, that I described before. It is still the form medium amplitude, laser amplitude. But the argument of this scattering amplitude is this nasty object, I dt plus h bar squared del squared over 2m. Okay?
So what you're doing now, you're postulating the new equation, or what you're doing? Because
I
you're
am
deriving from Gross-Pitievsky equation a new equation.
We have derived it, but for a talk I thought it's a bit too technical to describe it to you.
That separation, you see, you don't need to do in Gross-Pitievsky equation. You can solve without doing such a separation. If you're doing the operator form, you have to introduce all kind of high moments. That's correct, but you don't do the operator form of the equation, you do the wave equation. So that's not clear what you're doing.
I agree. From what I've told you here, it's not clear what I'm doing. I've been giving you the result. Okay?
We cannot evaluate the result.
So maybe I can hand wavy say why this functional form here. It's not that hard actually. What you would expect, the E that is normally in the scattering amplitude is the relative collision energy. So the way to look at this term is actually, it's more like the total energy minus the center of mass energy, because that's what exactly, this is the kinetic energy of the center of mass. Okay? Just that in deriving this, I had to go back and forth between energy and momentum, with time and frequency energy domain to make this work. Okay? I was just hoping that you would believe it or look it up to see how it's done.
Just a naive question about your approximation. So separating the wave function into the laser and the medium, you basically assume there's no particle transition between the two. So
That's correct.
particles remain either in the laser or in the...
Correct. There are lots of caveats on this derivation. Okay, this is one of them. But
Can you contrast this to just having a two-component condensate where you have, say, sort of a mean field for the first component and a mean field for the second component?
yes, it's related. The only difference is indeed that are my high collision energy, and I need to keep track of the energy dependence of the scattering amplitude very carefully. Most of these derivations don't have to worry about that. They can say the scattering amplitude is just a constant.
It's a contradiction because what you have there, you have a propagator that operates nothing else by the propagator, both space and time.
Yes.
And you're interested only in the energy, so you don't need a space-time. You don't need a space propagation, you don't need a time propagation. So you don't need to make it non-local, you make it non-local in time, if you want to do that.
I could have done that, correct. The only reason why I kept the spatial dependence, I keep carefully track of it, is that in most experiments these condensators still have a finite size. So it was very hard for me to imagine what would happen is I have a first, it's propagating in free space, then it has to go through the medium and then coming back out.
It's not clear, you don't seem to have a parameter to do something you see under control, a control approximation. So it looks like you're simply postulating an equation.
I agree with you. It is, on this talk, it is a postulation. The limits have to do mostly with the fact that I have to make assumption about how long the resonance lives. Well, I mean, I need to look at how long the wave packet, it takes the wave packet to go through the medium relative to the lifetime of the resonance, it turns out.
See, from the physics you described, you go from the open channel to the closed channel.
Sure.
So this is what you described at the beginning.
Uh-huh.
You see, the transformations you make here, you do all of them in the open channel.
Sure.
You don't do anything to the closed channel.
So
we
have integrated, I have integrated it out.
Have those here.
I have integrated those out, generating this object.
You didn't do that. You simply
I agree.
the Gross-Middleski equation. You didn't do that.
I agree.
Well, but I mean, Eite also said that in the paper there's a derivation, so maybe in the discussion in the afternoon we can learn a little bit more about the assumptions and the scales, and maybe we will sort of believe you for the moment.
Sure. At the end of the day, you'll find, I found at least, the answer is almost what I expected it to be. Almost. Okay, so next thing is also it's non-local in space and time. For a resonance width that is small compared to the energy of the collision, right, of the thing that comes out, I can linearize this f of v around the collision energy. So that's what's done here. Okay. So what's interesting in this case, you have a sort of like a constant value plus something like that's proportional to the derivative of the FDE. This is what I was aiming for, if you like. Maybe you would have immediately, as an atomic physicist, you would have removed this and put some kinetic energy operator here and say, well, it must be, because for slow light I had to do with sort of like the energy dependence or the frequency dependence of the index of refraction. Here I would like to know something about the energy dependence of the scattering angle. So I maybe expected something like this, that it's something of this form, okay? So final evolution equation. I have to do all kind of things, like the medium has to be big. I'm not going to have any transfer of particles back and forth. What else do I need? I'd also assume that the medium doesn't evolve, right? Because otherwise it gets more and more complex. And if you do that, then you finally get this Schrödinger equation, linear Schrödinger equation, as it turns out, for the laser propagating through the medium, okay? The neat thing is that it has all kind of weird things, that the mass of the particle becomes position dependent.
It's not gravitation.
Correct. We get something called the mean field potential. It is mean field GP-like, and it actually is proportional to the medium density times the scattering amplitude at the collision energy. If you're into GP equation, this is a term that you expect, right? It is the regular generalization of the GP equation, okay? But then another new term is that this one, which I will call V derivative, which is proportional to the derivative of the scattering amplitude at the collision energy times the density of the medium. And indeed, everything is complex. Correct.
It's not the potential, the kinetic energy.
However,
the kinetic energy is not Hermitian.
Yes, and it turns out there are losses. This is generating, so if you solve this equation, you'll lose particles rapidly. Okay. This is coming back to this thing I worried about before, that if you try to collide two clouds, if stuff comes out, I don't want that to happen. Okay? So maybe a little setback about energy scales, it might help a lot. So this is an energy scale from a nanokelvin to a millikelvin. Sort of our typical numbers in our field. Or if you like to choose your favorite atom, you can convert that to de Broglie wavelengths ranging from micrometer to nanometers. Okay? So what you need to know is that in lots of approximations in this delta function approximation, I assumed an S-wave limit. That is only isotropic scattering. That is around 100 microkelvin to 1 millikelvin in our field. Then we have collision energies between the wave packets, and I'm thinking around, say, 10 microkelvin, 1 microkelvin. That sort of collision energies I'm thinking about. Then I have the widths of these resonances. I can find in the literature widths that are in this region, sort of like 100 nanokelvin to 1 microkelvin. This is sort of kind of the scale that's working on. And then, of course, what I want to have these wave packets of the medium and the condensate needs to fit within the width of the resonance. And so they're sort of lying here. Those are also not unrealistic numbers. Okay. Okay, so let's go back to this it being imaginary. That is a problem. Okay. So in slow light and real light experiments, what I want to have is that the index of refraction changes fastest with frequency. That's when I can make slowest light. Okay. And it turns out that for those experiments, the losses at that point are minimal. That's sort of what I wanted to draw your point here. The losses are minimal. This is the absorption versus frequency. For atoms, we'd like to have that whole too. However, that's not really the case. So if you look at this graph again, this is the real part. That's the imaginary part. So you would like to use that point. That's where it's steepest. That's where I want to sit. But it turns out for near Feshbach resonance, the losses are maximal. So it's not a good idea to work there. So the neat thing for us is actually there exists what we call a lossless point near the resonance. The imaginary part of the scattering amplitude is 0 at that point.
Does that mean the scattering cross section is 0?
And so if you look at the real part, it actually is also 0. Yes. However, what I care about is actually the slope. The slope is still significant here. The FDE is still significant. So this is where I want to work. So yes, indeed, in red. Curiously, f of E is also, f is 0 at that point. It's the optical theorem, if you like. But what's interesting is that the slope is non-zero and actually fairly significant. And actually, if you follow these formulas, it's actually given by the background scattering length divided by the width of the resonance. Right? Suggesting that I really want to use narrow resonances. It's maybe not surprising, it's steepest, right? Okay. So let's simplify. Let's make a homogeneous medium just to begin with, to just practice on for me. In that case, that's this Schrödinger equation for the medium simplifies. First of all, of course, that Schrödinger equation becomes spatially independent. And the only thing that actually remains is the mass, m star. It's not the atomic mass anymore. Okay? But rather than plotting m star, I immediately would like to plot the group velocity. That is the velocity with which a wave packet propagates through the medium. Which in this case, the way you do that is you throw in a plane wave and take then the derivative of the energy, the dispersion, with respect to the wave number. Right? The energy is like k squared over m star. The group velocity is the derivative of that with respect to kappa, of the wave number. Okay? So that's what's plotted here in units of the free space velocity. Okay? So here there's 1 here, and then some smaller number. This indicating that in the medium I'm going slower. And the horizontal axis is sort of like the strength of my resonance, which I will call beta, which is basically nothing more than the FDE times the density of the medium. So it helps to make the density the medium denser, and it helps to make the resonance narrower. Okay? And then gray, if you like, the real formulas, right?
What happens if your resonance goes down to 0 and you go to infinity? Does it asymptotically go to 1/2?
So what are the limits? Indeed, for this particular case, and maybe I hadn't made this very clear, but I'm imagining that the medium and the laser are the same atoms. Indeed, we always have that it lies between a half and 1 times the original velocity. It becomes a half when the resonance gets extremely narrow or the medium becomes extremely dense. Okay? It is as if the Feshbach molecule with twice the atomic mass is being formed, is propagating through the medium, right? I'm imagining an atom goes in this medium, it picks up an atom, becomes twice as heavy. By momentum conservation, it needs to go half the speed. That's exactly that.
How about the energy?
The energy is conserved, hopefully. The other thing to actually have is that if you all look at all the numbers, beta can only be positive. Another corollary of it is, which is what I really thought about, I can't make fast atoms, the other analysis. I can always make atoms go faster, of course, in a simple way, but this is like if you can propagate through the medium, it cannot go faster. Okay.
So, another naive question. So the effective mass is essentially the particle's mass and a mixture of the molecule mass.
Correct.
So it's
Yes. And so the ideal would be to have take lithium and cesium or something, so that then the molecule gets the heaviest. Imagine a lithium colliding with a cesium condensate, and then you get a lithium-cesium molecule that's very heavy. Okay?
I have a question. You didn't understand the introduction. Do you expect, okay, if I have the picture of an incoming wave packet, the medium, and then another vacuum, you expect the packet to resume its original vacuum velocity after the medium?
Correct. It is forward scattering, yes. And I've engineered all these little things like there are no losses, which worried me a lot, right? Because I knew from an early experiment that if you shoot 2 condensates through one another, you're going to get 40% of the atoms scattering all over the place. You don't want that. Okay.
So if you could create not just a 2-body bound state, but a 3-body bound state, you'd expect to be able to get lower?
Yes.
To V0 over 2?
Uh-huh. Either that or use photons and then bind them to the medium and they go really slow. Yes. Sort of like we have a lot of like the microscopic limit of what slow light is in my mind anyways. The photon is so light anyways, so when it gets into the medium it gets really heavy. Okay, so now really have to worry about all kinds of things if you like, if you want to do, I don't know what this graph happened to this graph, but in real life there is no infinite medium, so we have actually finite size things. And so this is what I was trying to do here. We needed to see whether you can really see how much delay there is. Right? I mean, you can either talk in velocity slowing or slowing of the velocity about delay. So this is our attempt to do that. And this graph should have been something else. But what you did here in this case, you get a spatial dependent mass. It basically, there needs to be a transition between the atomic mass and the molecular mass, if you like. And then there is a trap generated by the medium itself, which is also proportional to the FDE. If you make the assumption that the laser cloud is kind of small, then it becomes a one-dimensional scattering problem in a potential given by this and a changing mass. And it turns out actually that this derivative potential is always smaller than the collision energy. So it's like it's not like scattering through a barrier, but you have to scatter over a barrier. I mean, the collision energy is higher than ever the barrier, that is higher than the barrier. So it's a relatively easy straight scattering problem. All right? And then you can ask for each plane wave that you shoot at it, sort of like what its phase shift is. What is the phase shift of every momentum through this thing? That's what that graph is supposed to show. And then the shift is nothing more than the derivative of the shift with respect to k. Okay? So we did that. We could do a WKB analysis of that problem, find it analytically. And the natural length scale turned out to be the size of the medium. So it's most natural to set how much spatial delay there is relative to the size of the medium. And we get this graph. Again, the inset was the graph before. This is the group velocity as function of sort of like the strength of the resonance or the narrowness of the resonance. And here what I've done is I plotted the same horizontal axis, but the vertical axis is that spatial delay of the wave packet. Okay. And in this case, what you'll find is that the delay must lie between 0, as if there is no medium, to 2 times the size of the condensate, the big condensate. It's also reflective of the fact that the velocity is a half, okay? Because you go at half the speed, and so if you have to go propagate through the medium of length L, your delay is twice that. Yes? Okay?
Can you, maybe you are going to do that, can you comment on the magnetic field stability that's needed, and what would happen if you don't quite have that stability?
Yes. We haven't done the serious, we're hoping an experimentalist smart enough might be able to do that very good, very well.
Do the analysis or do the experiment?
Do the experiment first, I would say. No, it should be straightforward. Because I know for that they can control this rubidium Feshbach resonance that I like a lot. They can control the magnetic field to 7 significant digits, so I don't have any worry about that, at least.
Who can control it to 7
Oh,
significant digits?
who? People that work with that Feshbach resonance, which is, for example, there's a group at NIST that does this. Maybe this is what I've shown here as 4 particular resonances, so whichever group is working on that particular atom. I don't know whether that's helping. But these resonances are probably like a 1/10 of a Gauss wide.
But if it would be different atom, it could be different way of control?
Yeah, different precision needed on the magnetic field. Okay. Okay. So for example, I put some numbers in here, like if you like a chromium resonance at 550 millitesla and the condensate is this dense, then you get a little bit of shift. If you use rubidium of that resonance, you get a little bit better results. Okay? Maybe this has numbers. So maybe this is better. This is actually summarizing everything in a table. Yes. So what is atom, the location of the resonance, and the width of the resonance. So you were asking about how controllable do you need this to be? Okay.
Yeah, I mean, I guess I'm still puzzled that you're saying the stability is better than 0.1 milligauss.
Oh yes, they must be able to do that.
Okay.
It's just a more expensive current supply. As a theorist, I can say that, right? Yes, I don't disagree. It is going to be hard.
Okay, that makes me happy.
Because the effect gets bigger the narrower the resonance is, right? Okay. So this is what you can see, right? This happens to be a resonance that's relatively broad in the scheme of things, and you can get the shifts of about 10% of the original size of the big condensate, which you might be able to see. This is getting harder for these red ones. They're extremely narrow. Okay, so there are kind of issues, right, with this problem. Is that unlike photons, atoms, if you have a wave packet of atoms, an atomic wave packet will spread. You just have a quadratic dispersion relation, so they will spread. So you need to be able to distinguish the spreading from the shift. Okay, that I see as more of a problem. And in addition, to hold these condensates, you want to know all the dirt, I guess. To hold these condensates, you need to have them in a trap. And now you have to decide: do I leave this trap on while I do this experiment? What else can I think of that can make it go wrong? Well, clearly I want to remove the traps, most likely. Okay. And then you were worrying about magnetic field control, but what about the collision energy control, right? It's the same question, right? You need to be able to make that wave packet. But now I know a group in New Zealand that can do this to 5 significant digits, they say. They can prepare, I think, a 1900 microkelvin beam of atoms with like a few microkelvin. That's only 3-4 significant digits, right? Microkelvin collision energy. I was amazed. And they basically do that by having 2 clouds in their individual trap, and then on top of that they put a gigantic parabolic trap. And they control the distance between the original clouds, and then releasing their original traps so that they roll down this weak harmonic trap, and they will have a very controllable collision energy. I'm always impressed as a NIST person if you can do something to 4 significant digits. Okay? I want to stop here. So you can look up this paper and the derivation here. And sort of an open question is also, so can I do this with something called an optical Feshbach, which is actually maybe a man-made Feshbach resonance. Magnetic Feshbach resonances are nature-made. You don't control in what system they are and what magnetic fields they occur. We just know that there are a fair number of them. This is the idea is making it yourself. And the idea is to have a resonant laser present that is resonance on the molecular transition, okay, to an excited vibrational level of a molecule. So you make your own Feshbach resonance. The downside is that these excited vibrational molecules tend to have a natural lifetime. They also like to spit out their photon again in a very nasty way. Not true for magnetic resonance. So basically my lossless point doesn't exist. There's never a point at which the imaginary part of the scattering amplitude is 0. And so then it becomes a question of, is there a balance where I can still do something? Okay. Thank you for your attention.